Hey everyone, in this video I'm going to be working through the first few problems of your second exam this semester. For this video I'm just going to be working through questions 1 through 5. These are all multiple choice questions, but I want to go ahead and break this down into several different videos so that you can kind of quickly move through this material. So your first question is, when conducting a 2D gel, the first dimension, as we discussed in class, is what type of gel? So in order to answer this question, you must be familiar with the process or the technique known as 2D gel electrophoresis. Now, 2D gel electrophoresis follows a process where you are going to first, or the way that we discussed it in class, what we are going to do is an IEF, or isoelectric focusing gel, in which case you're going to have a gel where you will load a protein sample onto it. That gel is a narrow gel here, and this orange blob right here is your protein sample. And what's going to happen is, as you send an electric current through that gel, these proteins are going to be able to separate. And they're going to separate through this pH gradient. So let's say that your pH gradient ranges from 9 to 7.5. Well, these proteins are going to migrate until they reach their PI, or their isoelectric point. And once they reach their isoelectric point, they stop moving. So your first dimension is isoelectric focusing. Your second dimension is SDS page. And so the cool thing about this technique is what you do is you take this gel right here that you've already run, this IEF gel, and you just place it atop an SDS page. And so you would have something that looks like this. That isoelectric focusing gel is here, so we've got a pH 7.5 to 9.0. And what you're going to be able to do is you're going to separate now by molecular weight. So your first dimension, your isoelectric focusing, separates by pH, and then your second dimension separates by molecular weight. Okay, so now with that information we can look back at our questions. Is what type of gel? Answer option A is a DNA gel. That's simply not right. This is a protein gel that we're using, or that we're analyzing. B, answer option, is a gel with a pH gradient that enables proteins to migrate until they reach their PI. Well, that's obviously the right answer, having just discussed that. Answer option C, a gel that separates based on their molecular weight. That would be your second dimension, your SDS page. So I'm just going to write second dimension. Answer option D, a gel that separates proteins based on their amino acid composition. We don't really know anything about our amino acid composition, and if you wanted to argue that that is the acceptable answer, well, it's entirely too general to answer this question. So that one's off the page. So we really, if anything, we should narrow it down to answer options B and C. And at the end of the day, that's just a matter of which one comes first. And the answer to that is your first dimension, your isoelectric focusing gel, separating based on, or separating with a pH gradient. Okay, so the peptide DRFKA would be, okay, now this question is really kind of addressing, this question is really just addressing whether or not you know, well, a couple of different things. First and foremost, it's giving you a peptide based on the single letter code. So you need to be able to convert that single letter code into the 3-letter code and ultimately into the amino acid sequence itself. So this should, at this point in the semester, become something that's a little bit second nature. D is aspartic acid, R is arginine, F is phenylalanine, K is lysine, and A is alanine. And this is, of course, read from N termini to our C termini. Okay, so we are reading it in that direction. Okay, now the question is asking, or the prompt is basically asking us, well, with that information, do we know where trypsin, chymotrypsin, and elastase cut? Well, before we go ahead and reflect on our answer, let's go ahead and do a little refresher. Trypsin is going to cut after positive residues, so something like lysine and arginine. at a physiological pH. Both of those R groups will be positively charged. Chymotrypsin is going to cut after a bulky residue like a phenylalanine or a tryptophan or a tyrosine. Okay, and then finally elastase is going to cut after small residues like alanine or glycine. Now when we look at this answer option and look at the identity of all of our different amino acids in this peptide, okay, we can ask ourselves, well, is trypsin going to cut? Do we see what we need for trypsin? Yes, we do. DR. After that R, trypsin is going to cut. After that K, trypsin is going to cut. So if we subjected this to trypsin digestion, it would be a DR dipeptide, FK dipeptide, and an alanine monopeptide, or the single free amino acid. Okay, chymotrypsin. Chymotrypsin is going to cut after these bulky residues. So now if we took the peptide DRFKA and we cut it with chymotrypsin, well, where is chymotrypsin going to cut? Chymotrypsin is only going to cut after that phenylalanine. So with chymotrypsin, we would get DRF and then KA. Okay, so both A and B, trypsin and chymotrypsin, will cut. Now, will elastase cut? Okay, now when you look at this, what you notice is elastase needs an alanine. Does this peptide have an alanine? Yes, it does. But that alanine is found on the C termini. So, term and I. Will elastase cut there? No, it won't, because there's no other part of, or there's no actual peptide bond that follows that alanine. So our answer options, well, A is true, B is true, and so then when we look down at our answer options D and E, this peptide would be cut by A and B but not C. And that is the correct answer. Answer option E is B and C but not A. Okay, so we ultimately, we're left with only D as a viable option. Okay, which amino acid is most hydrophobic? Now, this is a question that I believe that I gave everyone credit for. I cannot exactly remember at the moment. But if you look at all these answer options, okay, hydrophobic. Whenever you see a hydrophobic residue, what I want you to be thinking about is, well, something that's probably not going to do a lot of hydrogen bonding. I want you to see something that is lots of hydrocarbons. So if we think about the identity of all the different amino acids that we've looked at, well, I think maybe one of the more hydrophobic residues would be those larger amino acid R groups with nothing but hydrogen and carbons. Now, if we had something like a phenylalanine as an answer option, that would be great, because that's, well, that's just a phenyl ring, so that's going to be very hydrophobic. Looking at our answer options, arginine. Arginine is going to have a positive charge, so that's really going to be capable of any sort of hydrogen bonding or ionic bond establishment, so arginine's out. Aspartic acid, well, that's going to have that carboxylic acid group there, so that's going to be fairly hydrophilic. Histidine, same sort of thing as arginine. It's able to adopt a positive charge at a below a physiological pH, but it's still kind of dynamic residue. Tyrosine, well, tyrosine is like that phenyl ring that we want, but it's got that hydroxide group, so that's out. And ultimately, we're left with isoleucine, or if you want to think about the three in single letter codes, I, L, E, and I, well, this is just a hydrocarbon. So given these different answer options, really the only viable answer option is going to be E, because everything else can probably do some sort of hydrophobic or hydrogen bonding. So when it's most hydrophobic, that's what you would be looking for. If this question were asking for the most hydrophilic residue, well, that would be a little bit tougher to establish, just because of the fact that, well, once you eliminate isoleucine, you're left with a number of different residues that are fairly polar and can do some hydrogen bonding. Okay, a cation exchange chromatography column is composed of a large number of cellulose or agarose beads with a small molecule affixed to them, and that small molecule has a blank charge. Okay, so whenever you're looking at this sort of question and you are initially presented with a type of chromatography, a cation exchange chromatography column. What you should think is this is great for purifying positively charged molecules. Okay, so it's great for that. Now, in order to more or less capture a positively charged molecule, what do you need to have? Well, you're going to need to have something that will immobilize it. So you're going to need to have something with a negative charge. So this question is not even really going that deep, but instead it's just asking, well, in your column you have these beads, these largely inert beads, these cellulose or agarose beads, but you have something bound to them. Okay, and that something is going to be permanently bound there. Now, what that is going to be, that's basically your bait. You're going to be using that to basically troll along and try to find a molecule that you're looking for. In a cation exchange column, you are looking to bind a positively charged molecule. And therefore, this entity, this molecule that's bound to your cellulose or agarose bead, has to be negatively charged. Okay, so B is out, C is out, D is out, leaving us only A as a viable answer option. All right, tertiary structure and quaternary structure of a protein is determined predominantly by A, covalent bonds, B, backbone hydrogen bonds, C, ionic interactions, and D, none of the provided answer options are viable options. Okay, so this is actually kind of set up inventorying the different levels of protein structure. So your primary structure is dictated by covalent bonds, and those covalent bonds specifically are peptide bonds. Now, so that's not going to be the predominant force that drives the quaternary and tertiary structure of a protein. Backbone hydrogen bonds, however, well, now we're talking about our secondary structure. So we're talking about, does an alpha helix or a beta sheet form? Okay. And then we're down to answer options C and D. Ionic interactions and none can be provided. Well, ionic interactions, this is where you're talking about the interactions between different R groups. So side chain interactions. So how does an aspartic acid interact with, a sodium ion that's in solution? How does an aspartic acid interact with a positively charged arginine group within the polypeptide chain? And so ultimately, the answer to this question is C, ionic interactions. All right, well, I hope that this is helpful. I'm going to come back with another video going over a couple more problems in just a little while, but I hope this is helpful. Thank you very much.